Okay, so let's look at finding the eigenvalues and eigenvectors of a matrix. Okay, so this is what is happening. We're taking a point. This isn't a bold x, so it actually stands for a coordinate, xy. Okay? We're taking a point and we're applying a transformation matrix to it. And what happens is it stays on the same line, it just gets stretched along it, and lambda is our stretch factor. Marina?
For writing x, if we're writing x, are we doing again x with a line over? Or
X with a line under it, yeah. And it means a point xy. It's a vector. Yeah. Okay, so this bold x we'd write with a line under it, and it means a point xy. So we're saying we're applying this matrix to the vector, to the point, and it just slides further along the point. That's what we found here. Lambda was 3, they slid 3 times further along the point. Or the coordinate values got 3 times bigger. 1, 2, went to 3, 6. So there we go, we've got an equation, we just need to solve it somehow. Oh yeah, sorry, there's a note down there about that, about x in bold is shorthand for a general vector. Better.
No, I'm just thinking.
Okay, I'm going to show you the process for this because this is not straightforward. Okay, and the first time we do it, I'm going to show you the full kind of algebraic way of getting there, and then we will talk about the bit that you jump straight to when you're doing this. Okay, so there is a bit of algebra that is I would not expect you to just come up with. Okay, so this is what we're going to do. We are going to take the left-hand side. I think I'm going to write it as xy. I think that's, I'm more familiar with that. This is a scalar times xy, but I really want it to look a bit more like a matrix, so that both sides of my equation look more similar. So, what's the matrix I can multiply by that won't affect the size? The identity matrix, yeah. So I'm going to say this is lambda times a 2 by 2 identity matrix times xy. Okay, so all I've done is times one side by the equivalent of 1. No big change so far.
Why?
So that this side looks a bit more like this side, and it's going to help with solving it. Yeah? And actually, I could multiply the lambda into this matrix very easily, because it's just a scalar. So let's do that. It would be lambda 0, 0, lambda. Okay, so we've multiplied this side by the identity matrix, we've multiplied the scalar in. My next step is I'm going to subtract this, so it ends up on the other side. And I'm going to do 2 steps now. I'm going to do the subtraction first of all. And then the next thing I'm going to do is I'm going to kind of factorize. So I'm going to say, I'm going to take xy out as a factor. And I'm going to do this matrix minus this matrix, which will look like this. 1 minus lambda. Oh, that's a bit too much space, I think. 1 minus lambda. 4 minus 0. 2 minus 0, and 3 minus lambda. Better.
But how are we solving now? Because there are too many variables, right?
How are we going to solve this? There's a lot of variables. And what, sorry?
And only so much information.
And only so much information. Okay, folks, I want to reassure you, this stage is not something you will do every time you do this question. Okay? What we're going to jump to is called the characteristic equation. Okay? And that is the bit that we can go straight from basically this starting point, or actually this starting point, to the characteristic equation. Okay? The characteristic equation is the result when we say that we want this to be a singular matrix. We don't want it to have an inverse. Which might be something that you can't... Oh no, we talked about this at the start of the matrices unit. Do you remember what is true if we have a singular matrix that doesn't have an inverse? Did we talk about that right at the beginning? We did not. That was silly. Okay. If we want a matrix to not have an inverse, then we say the determinant is equal to 0. So the determinant of this is equal to 0.
Why does it not have an inverse?
How do we find the determinant of it? Got it, Marina? What is it?
AD minus BC.
Okay. So the determinant is equal to 0, which is AD minus BC. So AD.
But it's also the...
AD.
If you don't know how to calculate it, do you just put the lines on the side of it? Say if you're doing a 3 vector, because that's what it says here. Does that make sense?
Yeah, you can just
Okay.
write
Okay.
minus BC equals 0. This is called the characteristic equation. And this is what you are free to jump to.
And that's not the determinant.
It's the characteristic equation of this matrix. It's going to help us find the eigenvalues. Actually, I think this is where you would jump to. I'm going to put a little purple star here. Jump to this step. Yes?
But why does it not have an inverse?
Why?
Do we know that? How do we know that it's not having an inverse or should not have an inverse?
Can we tell why it shouldn't have an inverse?
Because we're assuming right now that it doesn't have an inverse, and I don't know why. Why should it?
I'm going to leave that with you to think about. We'll come back to it. Okay? I want to keep going through this if that's all right. So, we found the characteristic equation. Now, somebody said there's too many unknowns. This helps us quite a lot, doesn't it? Because now we've only got one unknown. How can we find that unknown quickly? Graph it, yeah, or use the solve app, however you want to do it. I think graphing it is how I'll probably go for it. And what is it going to find us? What does this stand for? The scale factor, and what's the new word I use for the scale factor? Eigenvalues. So can you find the, well, we're going to get 2 eigenvalues, aren't we? Because it's quadratic. Got them ready?
As a symbol, do we just put X in? Or do we need a specific
Which?
symbol?
No, just use whatever the variable is, doesn't matter. Okay, so I'm going to call them lambda 1 and lambda 2.
Maybe better. It's not.
So 5 and
There's 2 values.
5 and -1. Or the other way, I'm not sure.
Anisha, you happy with 5 and -1?
Yeah.
What? It doesn't matter which order we do them in. Yeah. The only thing we'll be careful of is when we find the eigenvector for 5, we'll write it with 5, and when we find the eigenvector for -1, we'll keep it with that one, so that they kind of correspond with each other. Everyone getting to the same point here?